Hi, I'm Jeff Bier from the Embedded Vision Alliance. I'm here today at the Alliance member company Aspera with founder and CEO Michelle Munson. Hello, Michelle.
Hi, Jeff.
Thanks a lot for joining me today.
Thank you.
So tell us a little bit about Aspera. First of all, what does Aspera do?
Well, Aspera has created a data transfer technology for moving bulk data over wide area IP networks. And that has grown into a general purpose platform for transferring what we would call big data sets that need both speed, reliability of transfer, and predictability, as well as security. We make a set of software applications around our core technology called fasp that allow for maximum speed and data transfer, secure access, and also easy end user experience in sharing large data sizes, sets of files, large files, and objects over distant networks.
Very interesting. And how did the company get started?
It was actually a garage house startup that I started along with Sherban Simu, the other founder. We set out first to experiment with and then create the FASP technology. Not sure if we were going to commercialize it, and then taking that out to a couple of key areas, which included video file transfer as well as intelligence data in the federal space. Got some very early interest in its capabilities and then decided to actually commercialize it. We bootstrapped the company, so this was 10 years ago, literally, and then have built it up over the last decade through a number of innovations in the core technology, the way it integrates with storage, and also the use cases. And we were recently acquired by IBM in January, so now we're a division of IBM Software.
That's an impressive success story. Congratulations.
Well, it sounds great in the compressed form. Sure. Lots of challenges along the way, but it has been fantastic.
I'm sure. So help me understand, as someone who doesn't have a background in networking, help me understand kind of what was wrong with how people were moving data across networks before Aspera developed its approach.
I think, first of all, there's a well-known problem, at least among folks that think about TCP networking, in essentially good utilization of long fat networks, meaning that TCP by design, which is the way that all data transfer is done reliably over the internet, has a built-in intrinsic bottleneck that makes the speed fixed and unable to be made better over a realizable throughput, especially slow and degrading over networks with higher latency and packet loss. So the long fat networks problem, right? In our case, I think breakaway from this that is so critical is the convergence of this problem with large data. Mm-hmm. And what we really set out to do is to try to attack the problem from what the data transfer needed. That is, the data sets are the critical entity that need to move. Secondly, this problem with efficiency is especially pronounced when the data sizes are large. And then lastly, the way you might choose to solve it, as in, is this something that's an accelerator that works sort of in the middle of the network, or is it an endpoint solution, mm-hmm. right, that's available to application software? That question influenced the way we approach the problem too, and we've really attacked it from the transfer of data problem space, meaning from the endpoint, and mm-hmm. Maybe we'll talk a little bit about that.
So is Aspera's technology implemented as software or hardware or both? So
it is software, and more specifically, it's application software. Mm-hmm. So the core technology, as well as the way users experience it, is application software or embeddable libraries that allow for data transfer and replace SCP, rsync, HTTP upload or download, Windows drag and drop, now desktop drive experiences, etc., built around FASP. And I think that's a really important insight to the problem, and particularly for this domain in embedded vision, because of the unstructured data sets. They're first of all, they're quite large. They're often in formats that are not really amenable to deduplication and compression techniques. Mm-hmm. And then lastly, a lot of the business driver for the data exchange is more ad hoc, meaning the file sets may need to be anywhere, and that could be from an end user to a back-end server storage, and that ad hoc nature really presses for an application solution.
That makes sense. So certainly video data tends to be big data. Yeah. It tends to be already compressed. And I know that Aspera's technology was recently used, I think, for moving some big video data
In the World Cup,
for the
right.
World Cup.
That's right.
Now, I think that was not streaming for real-time distribution, right? That was getting it from place A to place B
Right.
for editing or something like that?
Well, actually, it was in support of online streaming. This was a really interesting new use case. So our software is often thought of as the bulk data transfer solution. In this case, it was actually used for the transport of live video feeds, captured at the games, uploaded in real time through an Aspera session to our server software, writing the data out to Amazon's S3 storage. That stream that we were transferring was consumed in real time by an elemental transcoding system. This is all part of a product line provided by EVS, a very interesting sports broadcasting leader out of Europe. The streams themselves ultimately were transcoded and encoded at the same time, depending on what format it was, to online streaming formats that could be consumed on mobile devices as well as directly online by consumers. So this was a true end-to-end live stream case. You could think of it as a steady, reliable, highly efficient streaming protocol in this case because the cameras were in Brazil and the Aspera server software was in the Amazon region in Europe, for example. So quite a wide area, a lot of latency and packet loss to overcome. And the reason we were used is because, of course, the typical HTTP-based streaming would degrade significantly in throughput and couldn't keep up with the real-time pipeline.
So can you quantify those advantages?
Sure.
What does that look like in numbers?
Well, so a couple of things. So if you're thinking about global network distances, typical network performance for single TCP session is in the megabits per second. Clean networks, smaller latency, smaller losses into 100 megabits a second. Multiple streams are possible that might drive throughputs, particularly in really well-conditioned networks, to hundreds of megabits a second. What is not possible with traditional technology is to be on an ad hoc internet connection and have full line speed throughput regardless of distance. So that would range at the small end for a person on a very modest network doing typical upload download of maybe 2 to 3 times performance difference all the way up to hundreds of times performance difference. And we are often used for very high speed demonstrations over 10, 40 gigabit per second networks where at global distances the throughput difference is at least 100 times.
So purely through software you're able to effect a up to 100x improvement in throughput across...
Exactly, and it's all about the efficiency of the protocol. This isn't based on compression, it's not based on eliminating any of the data, it's based on the good put of FASP as it's moving bulk data over the network. So we don't lose any efficiency with latency or and then also have robust efficiency with packet loss. So packet loss has only the actual amount of packet loss effect on the throughput. And this leads to dramatically faster transfer times, and it also holds, and this is where the data set business comes in, it also holds for very large numbers of files and also very large file sizes. And that's really quite critical because most of what people think of as file transfer applications and protocols, due to the way host computers work, the way storage works, degrade badly as you get into file sizes that exceed the operating system caching effects, for example, et cetera. So those numbers are holding rather universally.
Really interesting. So, so you mentioned the Aspera software can be embedded, and I think one thing that's really interesting about this is if you really change the coefficient as you are about what you can do with the network, then it changes the math on trade-offs between what you do locally versus what you do remotely. And
Absolutely.
for example, in video surveillance, this has been a big conversation over the past 10 years about, well, should the intelligence be in the camera? Should the intelligence be in the cloud? Should it be in the closet at the facility? And one key driver to pushing the intelligence out to the nodes has been so much data, it's just very difficult to move so much data. Now, if you take that difficulty away, then that opens up
That's
some
exactly
different possibilities.
And this World Cup case is a perfect example. Basically, the captured video was aggregated across the world on the cloud for its processing, exactly as you've described, rather than trying to do the transcoding out at match and giving up all the scale out that you can get in the cloud environment, right? And to your point about video surveillance, our software is used precisely in this use case in some of the Intel applications that it's involved in. Right?
And so, given those types of applications, moving data over the internet, then security is going to be really important. So
Yep.
how does Aspera's technology
Address that,
the
yeah.
security needs?
So that area we felt always we need to just follow open standards and a complete security model. And so FASP is built off of a what you would call in strong crypto base in the OpenSSL framework in terms of the data transfer encryption. We also, of course, have a full stack that performs authentication of each session. We happen to use standard SSH and standard SSL depending on the variation in our products at that level. What's more interesting, I think, those are all expected behaviors, I think, in a technology like ours, is the access control. Because we're an application software, we also govern who has access to what data in our transfer software, meaning who can browse it and view it and who can move it. That access layer or access control layer is implemented across our products in a way that is secure and private, regardless of who the party is, fits in with enterprise authentication systems, including now SAML and OAuth and all the latest approaches. And then most importantly, in cloud environments where the storage is truly multi-tenant, ensures privacy of the user's access to their storage, independent of the fact that the same underlying storage may be used by multiple companies or multiple users. And what I mean by that is we implement our access control in our server software against the Amazon cloud, the Azure cloud, the SoftLayer cloud. It's built into Akamai in the same sort of way. So you can be assured that even though you're working in a multi-tenant environment, that if you're accessing your file data using our software, you and only your intended users can do that. Right?
Now, regarding embedding Aspera's technology, what kind of processing resources, memory resources are needed? You know, as
it's a great question.
The Internet of Things really expands very rapidly, we're getting to the Internet of often very small and expensive things that nonetheless generate a lot of data.
So maybe I'll answer that question from an example and move back to the sort of more formal description. The example is we've recently ported FASP to several embedded ARM processors, Raspberry Pi, BeagleBoard, for example, and this is in service to some of our customers who are making very low-cost video streaming and consumption devices. And of course, to run in that environment, the footprint of a transfer session in memory and CPU needs to be very low. And it is by design. I think that's another approach that we took to this problem very early on in how FASP is architected. The whole design is to use as little of the computer resource as possible, meaning minimal CPU footprint and minimal memory. We use a single session to transfer, unlike grid approaches that open up multiple sessions. Second thing is we attempt, in just the way the software is built, to keep the CPU usage as low as possible for the speed of the transfer. And a great example is recently worked with a customer at a standard Windows server, 3.6 gigabit per second transfers uploading to a CDN on one host computer and using 20% of the CPU, 20%. So very, very low consumption. And then the other piece is working politely on the network and the storage with the other applications. We have congestion avoidance built into FASP in the network path and in the I/O path. And that's really important because we're sharing the host resource and the network resource with other applications. Very, very different than accelerator solutions, which change the flow control of TCP, cause basically those accelerated flows to hog the bandwidth and distort the other traffic, not to mention the consequent behavior to storage of many, many streams, for example.
You're talking about approaches that use hardware accelerators to just speed up the TCP.
Yeah, to modify the TCP flow control, which is the classic technique in addition to dedupe and caching, right? Before, Aspera sort of entered this area.
And on a low-end processor like the ARM9 in the Raspberry Pi, what kind of throughput can you support?
Actually, it's terrific. The latest devices come with at least gigabit interfaces, and there is on those processors several hundred megabits a second, so approaching line speed and potentially full gig, depending on what exactly are the specs of the board.
That's really amazing.
It's true.
So where do you see this going in terms of the deployment of the technology? Obviously, it started with kind of infrastructure and enterprise type applications, but now you're working on embedded
systems,
Internet of Things types of applications.
The two go together. I think the most innovative and interesting direction for a company like ours is the convergence of what you just described. The fact that the average person's internet experience has become so dominated by connectivity, right? And the access to the data, and then all these innovative ways to get at that through the Internet of Things, and then combining that with the things people want to do, like data sharing, right? And so our engineering is really the two sides of that. It's the application platform to make it possible to do secure and easy to use data sharing, like you would think of sharing files with people, but coupled with, this emerging world of very ad hoc networked devices and computing platforms where people want to have their data and carry it around or collect it and send it back. Right?
Very interesting. So Aspera was recently acquired by IBM,
Yes.
and what does that mean for the future of this technology?
Well, that's part of the reason why I wanted to sort of bring up this convergence of the user case and the business need with the way the Internet of Things is evolving. Our purpose inside of IBM is very much that. It is to be a technology platform and to provide application software that does these things. So that's a very big mandate, because the range of customers is huge. It's everything from the most traditional enterprises that rely on largely secure data transfer, where the data sizes are getting bigger, all the way out to these emerging use cases that are very much driven by imagery and satellite data or social networking, and just have massive big data driving their business. What we're really commissioned to do here at Aspera is continue developing the platform, see that it integrates across the various infrastructure environments, and that would be all the cloud platforms, including SoftLayer, IBM's cloud, and then to continue offering, if you will, I'll call them clients, quote unquote, but ways of it getting at our software at the endpoint where the data is. And that could be just plain old good user applications such as Aspera Drive, Aspera Connect browser plugin, all the way out to embedded ports on ARM processors that, for instance, are used for video download and streaming. So this is kind of the broad mandate, if you will, for Aspera inside of IBM, and all of our work in engineering and productization is more or less around this.
Makes sense. Now, we've been talking about accelerating the movement of data over distances. What about just in a local context, within a building, or even within a chassis, where Ethernet is often the connectivity medium? Does this technology apply there?
It does to a certain degree. I think always one has to look intelligently at what the bottleneck is. And one of the things that everyone is working on in networking is eliminating some of the host and network stack bottlenecks, which are kind of the last point after you have fast pipe and you have great application transport, and you might even have fast storage like SSDs, for example. Then you realize it's the host architecture at the 10 gigs and above for packet processing that are the problem. So the reason I say, first of all, is in some cases where the critical factor is there is a whole domain of work to get above 10 gigabit networking in practice, right, throughout the data center. Now, data movement is often bottlenecked by the transfer application, even in the LAN. And the classic case is try to drag and drop a terabyte file on a Windows share, even if the Windows share is in your local network, right? It's a joke. It takes forever, it fails, and it's not something that you have control over in a repeatable way. So absolutely in these cases where the file transfer application, whatever it might be, like CIFS protocol or the actual FTP app is breaking down, right, which will happen even in the local area network, we are a great solution to that problem, right?
That makes sense, and that makes me realize, we've been talking about the kind of the real-time case, because that's sort of central to a lot of vision applications. But it's also true that the people developing vision applications often have massive amounts of data in the design process. For example,
Yes.
huge libraries of video that they use for verification purposes, huge design, databases, test results, and so on. And so I guess that's kind of where you guys got your start. Is,
Absolutely.
okay, maybe I have 2 or 3 development teams around the
That's
world
right.
working shifts, and I have this massive amount of data everyone needs access to,
Yes.
everyone needs to stay in sync.
Yeah, that's exactly right. And this is an especially good use case, first, obviously, for the technology, but I do want to call out, we have 2 products that are really interesting for this. Aspera Sync is a synchronization engine we built on top of FASP that avoids comparing files over the WAN like rsync, offers full bidirectional syncing, and is built on FASP. So ideal for synchronization of large file stores, and also it works across operating systems, so you're not boxed into a certain storage vendor, in addition to the fact that it's very fast. The other is our integrations into source code repositories. Very, very new thing for us. We're just now introducing a Git plugin for the Git repository that allows for using FASP as a high-speed byte stream plugin between the Git client and the server side. And this we really have helped build out with some of our key customers who are in exactly this space, because their source code repositories are how they work. They want a completely seamless experience, so they don't touch any alternative applications, and this has been a really great way to approach it. So this is something you're going to hear us talking more about.
Great. Well, that makes a lot of sense, and thanks a lot for taking the time to talk with me today. Coming in, I was a little clueless about how this was going to relate to the embedded vision world, but you've done a fantastic job putting it together. Thank you very much.
Really appreciate it. Thanks a lot, Jeff.
And we're going to have an Aspera white paper available on the Embedded Vision Alliance website, so look that up and learn more about the Aspera technology. Thanks again, Michelle.
Thanks, Jeff.